Hi y'all, welcome to today's video. In this video, we are going to be talking about an adiabatic reversible expansion. And in order to do that, I'm going to have to break the video up into 3 parts, with the first part being deriving the basic equation of statics for an ideal gas. So to start this off, let's say we have some very small differential volume of a fluid, and this fluid has a very, very small height that we will call dz. This fluid also has a cross-sectional area that we'll call A. And so before we do anything else, we're going to want to establish our positive and negative directions. So if we were to say that the upward direction was positive z, and that there was some position on our cubical representation of our fluid called position z, at the bottom of our fluid, then there should be some position that lies on the plane above position z that still lies on our fluid called position z plus dz. Since we started at z and just went up a height of our height dz. And so we can apply Newton's first law to this specific fluid. And we know Newton's first law to be F equals ma, where all of the forces that are acting on an object is equal to its mass times its acceleration. But this particular fluid is actually encased in a container that is much larger than itself, and thus this fluid is stationary. And because it's stationary, we know that its velocity and acceleration are both constantly 0. So if this fluid's acceleration is 0, then by Newton's first law, we know that all of the forces acting on this fluid have to equal 0. And so now we can start asking ourselves, well, what are all of the forces acting on this fluid? For this case, we're only going to worry about the forces that are acting on the top and bottom surfaces. So let's start with the bottom. Since this is a fluid, we know that there will be some pressure forces acting on it, and we know that pressure is equal to force divided by the area. So that means that force is equal to pressure times the area. And so since we know that there will be a pressure force, we can say that there will be a pressure force at position z, since it's at the bottom of our cube. And then we have to multiply that by the cross-sectional area A. Now what about the top? The top will be very similar. It will also have a pressure force acting on it, but instead of this force being at position z, obviously it will be at position z plus dz. And we also have to note that this pressure force is acting in the downward direction. And since we established that the upward direction was positive, then we know that this pressure force acting on the top surface is negative. And we also have to multiply that by the cross-sectional area as well. And we also have to consider the gravitational force that's acting on this fluid, which will be equal to the weight of the fluid, and that is its mass times the acceleration due to gravity. And it's acting in the downward direction, so it's also negative. So now that we have listed all of our forces, we can go ahead and apply a force balance to the fluid by adding up all the forces and setting them equal to 0, since we established that all the forces have to equal 0. So I'm going to start with the bottom pressure force, pressure at Z times the cross-sectional area A, minus, since it's negative, the pressure at Z plus dZ times the cross-sectional area A, once more, minus our weight, the mass of the fluid times the acceleration due to gravity, and all of that is equal to 0. And so now I'm going to do a little bit of algebra. I will factor out a negative area from these two terms so that we can have our pressure at Z plus dZ be positive, and then I'm going to add our mg term to both sides so that we're left with the negative area times the pressure at Z plus dZ minus, since this is positive, we have to make it positive, the pressure at Z is equal to the mass times the acceleration due to gravity. And so now we don't really have any apparent direction. So what we can do to kind of combat that is notice that the equation is asking for the mass of the fluid, and we don't have that anywhere. But we do know that mass is included in the equation for density, with density being the mass divided by the volume. So if density is mass divided by volume, that means that the mass is equal to density times the volume. And we don't explicitly have the volume either, but we do have the cross-sectional area and the differential height dz, so we can replace that for our volume. So that we're left with the mass is equal to rho times the cross-sectional area times the differential height. So we can plug this back in to our equation so that we have it equal to rho times cross-sectional area times the differential height, and we can't forget the acceleration due to gravity. So clearly we have we have the area in both terms on each side, so I'll divide a negative a term, or a negative a variable, so that we're left with the pressure at Z plus dZ minus the pressure at Z is equal to a negative rho times the differential height dZ times the acceleration due to gravity. So from here, I'm going to divide both sides by the differential height, or could even say the differential thickness dZ. And this leaves us strictly looking at the left side with the pressure at Z plus dZ minus the pressure at Z divided by the change in height of our fluid. And why this is great to have is because we noted that we had a differential height or differential thickness of our fluid dZ. And the change from position Z to position Z plus dZ is that thickness, or is that change in height. And so if that height of the fluid is exceedingly small, so small that it is our differential thickness, then we can also conclude that the pressure at Z plus dZ minus the pressure at Z is also a very small differential change in pressure. And so we can label, or we can call our numerator dP for the differential pressure and divide it by the differential height or differential thickness dZ. And now we have created the change in pressure with respect to height equation for our fluid. And that'll be equal to negative rho times acceleration due to gravity. And so now that we have this lovely differential equation, we can start to relate this back to the ideal gas law. And we know the ideal gas law to be PV is equal to nRT, where P is pressure, V is volume, N is number of moles, R is the ideal gas constant, and T is the temperature. And so bringing back our density equation, where rho is equal to the mass divided by the volume, we also know that when referring to ideal gases and mass in moles, you can refer to the mass as the number of moles times the molecular weight, because it'll give you the same units. You'll still end up with a mass. So this can be equal to N times capital M divided by the volume. And so having this information, we can rearrange the ideal gas law for the volume such that it's equal to nRT divided by P, the pressure. And we can put this new ideal gas law equation into our density equation, so that the moles times the molecular weight is now divided by the number of moles times the ideal gas constant times the temperature. And since it's divided by P and it's in a fraction, we can go ahead and multiply that on top. And we can cancel the two number of moles terms out. And then we're left with density is equal to the molecular weight times the pressure divided by the ideal gas constant times the temperature. And so now that we have this new expression or equation for density, we can put this back into our differential equation. And we are left with the change in pressure of our fluid with respect to its thickness or height is equal to the negative molecular weight times the pressure times the acceleration due to gravity, all divided by the ideal gas constant times the temperature. And this is the basic equation of statics for an ideal gas. So in part 2 of this video, we are going to be exploring how pressure and temperature of an ideal gas relate during an adiabatic reversible expansion. And to do that, we'll have to refer to the first law of thermodynamics, which states that the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. Where the work is equal to the external pressure times the change in volume. So differentiating the first law of thermodynamics will give us du is equal to dq minus p dv. So if you imagine we have a pocket or a bubble of air, and this pocket of air begins to rise, change altitudes, elevate, and goes up, and then it expands. And once it expands, it does work on its surroundings and has some pressure inside of it. If this bubble rises slowly enough, the pressure on the inside will be able to remain equivalent to the pressure of its environment, or the external pressure. And this is what we know as an adiabatic reversible expansion. Adiabatic meaning there is no heat added to or removed from the system, and reversible meaning that the pressure internally and the pressure externally will be the same. And so since as I said, it's adiabatic, there's no heat added to or removed from the system, then we know that dq will be 0. And it being reversible, this is P external. P is equal to P external. So we can rewrite the first law of thermodynamics equation that we derived to be du is equal to negative P dV. And so since there is no heat added to the system or taken away from the system, we know that all of the changes in internal energy will be due to changes in temperature, and we can say that the changes in internal energy are equal to the specific heat, or the heat capacity at a constant volume times dt, or the change in temperature. And so now we have a new expression for du, which we can replace so that CV times dt is equal to negative P times dV. But we also know, per the ideal gas law, that PV is equal to nRT, and if we rearrange it for pressure, we'll be left with P is equal to RT divided by V. And I did omit the amount of moles from this new expression, but it's reflected in the volume such that the units are cubic meters per mole rather than just cubic meters. So it's still in there. So yeah, now that we've done that, we can plug this back into our equation here and rewrite it so that it becomes negative RT divided by V times dV. And so I can do something really nice and divide both sides by T so that I'm left with CV times dt divided by T is equal to negative R dV divided by V. And this clearly gives us two derivatives of our temperature and volume, which we can integrate. And the reason we would want to do that is because we want to be able to show or to reflect the changes in our two states of air. And so if we imagine that this is our first bubble of air, then all of its parameters and components, the pressure, temperature, and volume, we could refer to as volume 1, pressure 1, etc. And refer to all the parameters for our second bubble as V2, P2, etc. And so coming back here, we can now integrate these integrals from T1 to T2 and V1 to V2. And so doing this, we'll get the constant volume times the natural log of T2 divided by T1 by just doing simple log rules. And that's equal to negative R times the natural log of V2 divided by V1. And so I'm going to divide both sides by the constant volume and then take the exponent of both sides so that we can get rid of the natural log. And then we're left with T2 divided by T1 is equal to V2 divided by V1 raised to the negative R divided by CV since we took the exponent. And this looks a lot better. We're getting a more explicit relationship and seeing how things relate. But as I mentioned, we want the relationship of pressure and temperature, not volume and temperature. And we can kind of verify that by realizing that in our basic equation of statics for an ideal gas, there was no volume term or variable, but we did see pressure. So we're going to want to reflect that in this relationship as well. So to do that, we really don't have to do much work except utilize the ideal gas law. And to make it even simpler, we just have to swap the pressure and volume so that volume is equal to the ideal gas law times the temperature divided by the pressure. And so this relationship stands for the volumes and temperatures and pressures of both of our pockets of air, our bubbles of air. So we can list this first equation as V1 is equal to R times T1 divided by P1, and then we can create another that is identical except it relates to our second bubble. So it's V2 is equal to R times T2 divided by P2. And so by doing this, we can now bring this equation up here and rewrite it with the substitutions of our volume variables. So we have T2 divided by T1 is equal to V2, which is T2 divided by P2. We're gonna omit the ideal gas constant because it'll cancel out. So we have T2 divided by P2, and then divided by T1 divided by P1, but we'll just multiply it by the reciprocal so that it's P1 divided by T1. And we have to raise this to our exponent of negative R divided by CV. And so from here, we can do some more algebra, clean it up even further. And the way we're going to do that is by multiplying both sides by T2 divided by T1 to a positive R divided by CV. So I'm going to move this over here. So you know that's that. But yes, the reason why we'll be able to do this is because by multiplying both sides by T2 divided by T1 to the positive R divided by CV, we're able to completely cancel out the T2 and T1 terms on the right side and isolate our P1 and P2. Which just leaves us with P1 divided by P2 to the negative R divided by CV. As for the left-hand side, well, if we multiply this by T2 over T1 to the R divided by CV, then we're able to create a new exponent because the power for this term here is 1. And so when we multiply the exponents, we're simply adding them, and that will give us T2 divided by T1 to the 1 plus R divided by CV power. So we can even simplify that further and just combine the terms of in our exponent. Since 1 would be equal to CV over CV, we're left with CV plus R divided by CV. And so we are going to want to get this relationship in explicit terms of the temperature so that we're not left with any exponents. So to do that, I'm going to multiply both sides by the reciprocal of our exponent on our temperature terms, which will be T2 divided by T1 CV plus R divided by CV times CV divided by CV plus R, and multiply this side by the same thing. So this exponent completely cancels out. We're left with T2 divided by T1 is equal to P1 divided by P2. The numerator denominator cancel out, so we're left with to the negative R CV plus R. And this leaves us with the relationship in how temperature and pressure of an ideal gas behave and relate to each other during an adiabatic reversible expansion. On to part 3. So for the third and final part of this video, we're going to be talking about how pressure and temperature of an ideal gas independently are affected or relate to the change in altitude during this expansion. So first we should recall the 2 equations that we derived, which was 1, the basic equation of statics of an ideal gas, and 2, how pressure and temperature relate to each other during the adiabatic reversible expansion. So we know that the basic equation of statics was the change in pressure with respect to the change in altitude is equal to the negative molecular weight times the pressure times the acceleration due to gravity divided by the ideal gas constant times the temperature. And then we know that our pressure temperature equation was the second temperature divided by the first is equal to the first pressure divided by the second to a power of negative R divided by CV plus R, where R is the ideal gas constant and CV is the specific heat capacity at a constant volume. So to start, we're going to want to make one modification to our temperature equation, and that is instead of having T2 and P2, we're just going to call them T and P because we've acknowledged that T2 and P2 were just the temperature and pressure after our air has experienced a change in elevation or a change in altitude, and that's already been reflected in the basic equation of statics. So, you know, we're doing it for consistency and understanding of the state of the air. And so now that we've done that, we can rearrange our temperature equation to solve just for the temperature after the air has been elevated. And that'll be T is equal to T1, since we just, you know, divided or multiplied by both sides, times P1 divided by P to the negative R divided by CV plus R. So I can tell you we are going to be writing this exponent a lot. So to make it easier and more efficient, I'm going to assign the exponent to a variable that I'll call omega, just so that we don't have to keep writing negative R divided by CV plus R. So omega is equal to negative R divided by CV plus R. And we can rewrite it so that it's just T is equal to T1 times P1 divided by P to the omega power. So from here, we can come back to the basic equation of statics, and we see that now we have an equation for our variable T. So I'm going to plug that in, and we get the change in pressure with respect to altitude is equal to negative M P times G times R times T, but T is actually T1 times P1 divided by P to the omega power, but it's in the denominator, so we'll multiply by the reciprocal so that it's P divided by P1 to the omega power. And so you'll notice we already have a P term in the numerator, so I'm just going to combine the two, which will give us negative M times G times P to the 1 plus omega power divided by R times T1 times P1 also to the omega power, and this is still equal to dP over dZ. And so we're going to want to set up this equation to be ready for integration, so we can actually reflect how pressure and temperature change with respect to the change in altitude. So we need to divide both sides by this pressure term, and then multiply both sides by our dz term. And so that will give us P to the negative 1 minus omega times dP is equal to negative M times G divided by R times T1 times P1 to the omega times dz. And so now we're ready to integrate. We can integrate this term on the left, and since all of this is essentially a constant, we can integrate dz. And so where do we integrate from? What parameters do we use for integration? Well, as we said before, we have some bubble of air, pocket of air that elevates and expands, and this pocket of air starts at initial values P1, V1, T1, etc. And since we have pressure equal to our right hand side, we are going to label our parameters for the first pocket P1, and we're wanting to see how that relates to the change in altitude, so we'll label our initial altitude Z1. And after it experiences this change in altitude, it will reach some final pressure or final altitude, and so we can label those as PF and ZF. And so those will be our limits of integration. So we can integrate the first integral from P1 to PF, and the second from Z1 to ZF. And so from here, this integral leaves us with -1 over omega times P to the negative omega, which is equal to, well, we have to actually evaluate it from P1 to PF. And then that's equal to the right-hand side, which is still our constants, -m times g divided by r times T1. And since we have the P1 to the omega in the denominator, I'll take it out of the denominator by raising it to a negative omega. So we have P1 to the negative omega, and we're integrating dz from ZF, or from Z1 to ZF, but it's just dz, so we can just multiply this by ZF minus Z1. And so now we can actually evaluate our left-hand side, which gives us -1 divided by omega times PF to the negative omega minus P1 to the negative omega. And then I'm going to take this P1 to the negative omega and just put it to the front so that it's negative P1 to the negative omega times mg divided by r times T1 times ZF minus Z1. So from here, you'll notice both sides of our equation are negative, and we have a fraction on the left, and we can easily get rid of that by multiplying both sides of the equation by negative omega so that both sides of the equation become positive. And that leaves us with PF to the negative omega minus P1 to the negative omega is equal to P1 to the negative omega, and now we have to multiply our constants by omega, which is omega times mg divided by r times T1 times ZF minus Z1. And so now we're still doing basic algebra. We can add this P1 to the negative omega to the other side, since we already have one on the right-hand side. And that leaves us with PF to the negative omega is equal to P1 to the negative omega times 1 plus omega times mg divided by r times T1 times ZF minus Z1. And if we want to get final pressure by itself, all we have to do is take the reciprocal of the exponent for every single term. So we'll just multiply each term by -1 divided by omega. So we're left with PF is equal to P1 times 1 plus omega times mg divided by r times T1 times ZF minus Z1. And we have to raise everything in the parentheses to a -1 over omega. And so this is our final equation for pressure and how it relates to the change in altitude, but we need to substitute in our equation for omega, since we didn't want to have to keep rewriting it over and over again. And so that gives us the final pressure is equal to the initial pressure times 1 plus omega, which is -r divided by CV plus r. And so we have to reflect that by making this entire term negative. It's a fraction within a fraction, so the r's will cancel out in the numerator and denominator, and we'll be left with a CV plus r in the denominator. So it's minus the molecular weight times the acceleration due to gravity times, or divided by the constant volume times the ideal gas constant times the initial temperature. times the final altitude minus initial altitude, all to a power of -1 over omega, but omega's already negative and a fraction, so we just have to take the reciprocal of it, which leaves us with CV plus R over R. And this is how pressure is affected when a change in altitude of an ideal gas occurs. And so now all we have to do is find our temperature equation, but this should be much easier because we already have one, and we can rewrite it below our diagram for our pockets of air. So much like how we rewrote our parameters for the pocket of air after it's been elevated, for pressure and altitude, we can do the same for temperature. So this will be T1 and up here will be TF, and so we can reflect that in this equation. So it's the final temperature is equal to the initial temperature times the initial pressure divided by the final pressure to omega. And so we have derived the equation for the final pressure, which we want to input into our equation for the final temperature, but this is an extremely long equation and it would probably take us a long time to do. But it does work out wonderfully when we do it algebraically, and I'm going to break it down so that it makes more sense and gives us the same outcome. So since we have PF in the denominator and you come back to the pressure equation, you notice that there's already a fraction within that and an exponent. So what we can do is set PF equal to P1, so we'll keep the P1, but everything in the parentheses we will call X. And we'll keep the exponent as -1 over omega. So PF will be equal to P1 times X to the -1 over omega. And so if we plug this into our final temperature equation, this gives us TF is equal to T1 times P1 divided by P1 times X to the -1 over omega. And then all of this has to be raised to the omega power. And so immediately you'll notice, okay, well, P1s cancel out, so we're left with a 1 in the numerator. But since X is in the denominator and raised to a -1 over omega power, well, anything in the denominator is already already has a negative power, and since it's explicitly negative, the negatives cancel out and now it's positive, so we can put it in the numerator. So this leaves us with T1 times 1 times X to the -1 over omega, and then all of that has to still be to the omega power. So 1 times X is just X, and or excuse me, this is actually positive since we took it out of the denominator. 1 times X is X, and we have to multiply the exponents. So omega times 1 over omega is just 1. So all of this leaves us with T1 times X, and that will be equal to TF. And we said that everything in the parentheses would be equal to X, so our equation for the final temperature is equal to the initial temperature times 1 minus the molecular weight times the acceleration due to gravity divided by the constant volume plus the ideal gas constant times the initial temperature times the final altitude minus the initial altitude. And since X was everything in the parentheses, we don't have to raise it to a power. And this gives us our equation for how temperature relates to a change in altitude of an ideal gas during an adiabatic reversible expansion. So throughout this whole video, we have achieved three things. The first thing we achieved was deriving the basic equation of statics for an ideal gas. The second thing was the pressure and temperature relationship of an ideal gas during an adiabatic reversible expansion. And our final thing was how pressure and temperature independently are related to a change in altitude of an ideal gas during an adiabatic reversible expansion. Thanks for watching.